Hello everyone, thank you for coming today. So today I'm presenting a part of the work that is described in my habilitation thesis, and the content of today's lecture goes under the title Ranking on Manifolds for Visual Search and Object Discovery. So humans are easily able to tell whether two objects or scenes look alike. And the same ability for a computer vision algorithm is very important because it is associated with real-world applications. So as visual similarity, we refer to the estimated degree of relevance between objects, scenes, or stuff that are depicted in two images. Mathematically, it is a function that takes two images and outputs a real value, a real number. So the definition of the relevance is typically application dependent, and it often comes in a binary form. A pair of images is either relevant or not relevant. So for instance, in different contexts, so two images can be considered as relevant if they originated from exactly the same photo, otherwise not relevant, if they depict the identical object, the same particular object, which has been also like a major focus of our work, or depicting the same species, and so on. So visual similarity, as estimated by computer vision algorithm, gives a continuous similarity value that we want to be high for relevant image pairs or low for non-relevant image pairs. And there is a very common way to estimate visual similarity, which is with a two-step approach. That first, we map images to a high-dimensional representation space. This mapping is called a representation model. It can be either handcrafted or learned according to the application. And as a next step, to estimate visual similarity, we simply rely on standard metrics in this high-dimensional space. For instance, Euclidean distance, to estimate the visual similarity, which is also a very efficient metric to estimate, which takes us to the task of visual search. We're given a large collection of images, what we refer to as database, and a query image. We have an efficient way to estimate visual similarity between the query image and all the images in the collection. Then we rank based on the Euclidean distance. That's what we often call Euclidean search. And we get the top-ranked results, which can often contain useful items depending on the application. Just to motivate the usefulness of visual search, I'll give a couple of application examples. For instance, Bing Visual Search, that is a visual search engine provided by Microsoft Bing Online. You can go there, upload an image, and see the top returned results, which are also accompanied by the relevant websites where these images are found. So in this way, someone can find more information about the origin of the items, of the objects shown in the image, or end up with an online shop where this product can be purchased, and so on. Or another application example where visual search is often used for localization. We have a query image, and by finding the most relevant images with visual search, any knowledge that accompanies these images can be potentially, with some further processing, transferred to the query. And this is, for instance, the case in the case of GPS information, where the geotags of the relevant images are used to geolocalize the query as well. Now, going one step further, given a large collection of images, we're not only querying with a single image, but we query with all the images. We cross-match essentially all the images in the collection, and we construct a similarity graph by establishing links between the most relevant items. With further processing, this allows us to discover groups of similar objects that not only enables applications such as organization and browsing of photo collections, but maybe most importantly can be input to further processing to follow-up algorithms. So in the work that is described in my habilitation thesis, we're dealing with concepts and tasks that I just described, namely representation, similarity, search and discovery, object discovery. While today, I will focus on the tasks of visual search and object discovery, with a goal to feed the output of different types of object discovery to facilitate other tasks, classification and representation learning tasks, that are dealing with limited amount of supervision. And in all this work, there is a common factor that I will first like to motivate. So initially, we assume the representation model that is given. That means we map all images to points in the high-dimensional representation space. Let's consider a toy example shown here. And then, for a particular query image, as said, we can easily estimate the Euclidean distance to all other points, rank based on that, and perform visual search. The problem is that Euclidean distance is typically locally a good measure and not globally. And this is the case because relevant objects in images tend to appear nonlinear manifolds in the representation space. Some of the reasons for this to happen is the different conditions under which the objects appear. Different viewpoints, different illumination conditions, a lot of background clutter, occlusions, and so on. Therefore, it seems important to obtain a similarity measure that takes such manifold structures into account, and therefore perform the ranking based on that. So that's what we refer to as manifold similarity. And ranking based on that is what we call ranking on manifolds, and in this first part I will describe how to use this for the task of visual search. So here is an existing way to estimate such manifold similarity proposed by Zhu et al. In 2003. We assume the representation model to be given. We map all images to points in the representation space. We have a database of n examples. And in an offline step, we construct a k-nearest neighbor graph of the database images. Now, during the online step, for a particular query, we want to spread, to propagate the similarities over this graph. And here is an iterative solution to obtain such similarity. So this vector f here is an n-dimensional vector that consists of the similarities between the query and every image in the database. Then we have a sparse similarity matrix that essentially represents the graph. And with multiplication between this and the similarity vectors, we perform the spreading. For every single query, we have a different vector. The query is considered part of the graph, and the vector that represents this query. And finally, a hyperparameter that defines the amount of spreading that is performed over the graph. Let's rather have a look at the toy example to understand how this similarity measure works. At the initial stage, we have constant similarity for all the points, and we start to perform the iterations, iterate more and more, and refine the similarity. So it's easy to observe here that points that belong to the same manifold as the query point have higher similarity. And this is quite different than what Euclidean distance captures. Now, in terms of a visual search task, if we use this similarity to perform the ranking and retrieve the relevant images, in practice, just to briefly mention that we obtain a large performance boost compared to simple Euclidean search. On the other hand, it is much more costly to obtain and estimate such a similarity compared to simple estimating Euclidean distances. There is also a corresponding closed-form solution to obtain the same result. However, the problem here is that there is a matrix that is involved that is not sparse. Let's recall that we are dealing with k-nearest neighbor graphs, therefore the corresponding similarity matrix is sparse. And the problem is in large-scale setups, where we have a large collection of images, with estimating and actually essentially storing such a large matrix. So this is an efficient solution only for very, very small-scale problems. Instead, in our work, we observe that one can equivalently solve the corresponding linear system. The benefit is that now we're dealing with a sparse matrix that we can store even for large-scale problems. And another benefit is that there are solutions of preference, such as the conjugate gradient, which is the iterative numerical solution to solve this linear system. So it's a preferred solution for this kind of linear systems. In practice, it converges much faster than the original iterative solution. And both these methods are what we call online methods, because the costly part to estimate the similarity is done during the query time. This iterative process is performed during the query time. We go one step further in our work and use a low-rank eigen decomposition of the matrix that is involved. There are approximate methods in the literature that allow us to do this at large scale, and this allows us to revisit the closed-form solution. And now we can obtain an approximation of this similarity measure only with vector to matrix multiplications during the query time. And this is what we refer to as offline approach, because the costly part for obtaining this manifold similarity is done during an offline stage, and it's common for all the queries. Can also be seen as storing one embedding per image. So this allows us to have efficient search for problems that are larger than those of the closed form solution. Still, at much larger scale, it has drawbacks because the rank of the low rank approximation needs to be high, therefore the dimensionality of these embeddings needs to be high, and we have larger memory footprint. Finally, another contribution in our work is a hybrid approach, where we first perform the offline approach for low-dimensional embeddings, therefore small memory footprint, and the online approach gets the result of the previous step as an initialization, and therefore we are able to only to get a good result only with few iterations of conjugate gradient. Now, just to briefly mention that this hybrid approach offers a good solution in the trade-off between performance, memory, and speed, because it has good performance for relatively low query times, and good performance despite not requiring a large amount of memory. Now, again, in the context of manifold similarity for visual search, a different kind of contribution is about finding small objects. So far in what I described, we're dealing with global image representation. That means we're using one vector per image, and this in practice fails to find small objects. Instead, in our work, we use region representation, meaning we use one representation vector per square region and sample multiple regions. Now, one issue is that to obtain manifold similarity becomes more costly. We're dealing with larger graphs, and we have multiple query vectors for all the regions in the query. So what we do, we propose how to form and solve a single linear system instead of multiple linear systems for all these query vectors. In practice, what happens is that performance is significantly improved, especially for small objects that are now retrieved in top-ranked positions, while otherwise, with a global image representation, they are missed from top-ranked positions. Now I'm switching to another part of this talk, where a similar concept, similar methodology for ranking on manifolds will be used to perform different types of object discovery. And the result will be fed as input to facilitate other tasks. First is the task of self-supervised representation learning. So the question that we ask is, since this manifold similarity is a better similarity measure than Euclidean distance, can we retrain a representation model so that Euclidean distances in the new representation space will imitate what manifold similarity does in the original space? And the task formulation here is as goes. We're given a large image collection, no labels provided by humans. And we start with a pre-trained representation model. For instance, one that is trained for some generic task, typically training on images for classification. And then the task is to fine-tune it for a different task without using any labels. And the way we approach that is to perform object discovery, so for particularly selected query images from this collection, to automatically discover positive and negative images with respect to these queries. That is, we obtain relevant and non-relevant image pairs. And then we use these pairs as training examples for representation learning. We simply rely on standard representation learning methods that try to map relevant images in nearby points in the representation space and non-relevant images in faraway points in the representation space. So now let's have a look at how this discovery process is performed for a particular query. We rely on the manifold similarity as a trustworthy signal for supervision, and we contradict this with Euclidean distance. In particular, we focus on the regions that matter, the ones around the queries. So the positives are chosen to be the examples that are neighbors with manifold similarity, but they're not neighbors with Euclidean similarity. That means manifold similarity indicates that this point should be nearby, but Euclidean distance at the moment, the current representation space does not capture that. Therefore, they should be mapped closer in the new representation space. In a symmetric way, we also select the negative examples. And these are the Euclidean neighbors that are not manifold neighbors. So here, Euclidean distance indicates that these points are currently nearby, but manifold distance indicates that they should not. Therefore, they're chosen as negatives to be pushed apart. And now let's have a look. How does this look when we perform this algorithm on a large collection of 1 million images? Here we saw some sample queries and the selected positives with our approach and with a trivial approach that chooses positives as simply the nearest neighbors with respect to Euclidean distance. In both cases, these are truly positives. They depict the same object as the query. The difference is that we observe that we have more challenging cases, more challenging viewpoints, for instance, with the proposed approach. So therefore, these are most useful as training examples. Correspondingly, for the negatives, we contradict them again with a trivial approach of choosing as negatives the images that are not neighbors with respect to Euclidean distance. Again, in both cases, these are truly negatives. But the difference is that in our case, we have different objects that tend to have similar patterns with the objects depicted in the query. And the high quality of the selection holds also for different kinds of objects that tend to repeat in the large collection. The achievement here is that without using any supervision by humans, any labels provided by humans, we end up to create high quality, hard and challenging pairs that can be used for training. For instance, someone can see that some of the negatives are even difficult to disambiguate even for a human, where we have objects such as this one that look really similar to the query, but there are some distinctive details that make the difference. Once these pairs are selected, then we use them to retrain the model and evaluate it for visual search. We see that compared to the initial model, we see significant improvement in terms of performance on different datasets on different kinds of objects. We also compare this approach with an earlier approach that uses 3D reconstruction, automated 3D reconstruction, to automatically collect training examples. So this tends to work for objects such as buildings and landmarks, but not necessarily for other objects that our method works on. Now switching to a classification task for the first time of this talk in a semi-supervised learning setup. So the final task that we want to solve is to train a classifier with a training set that contains both labeled and unlabeled examples. And we're dealing with an inductive setup, meaning we want to obtain a classifier that we're able to use to make predictions for future unseen examples. We define a proxy task to approach first. It is to perform transductive inference, meaning that in this step, we don't care about obtaining predictions, any classifier for predictions of future unseen examples. We only care about making predictions for all unlabeled examples of this fixed closed training set. And we perform this again by relying on manifold similarity to propagate labels from labeled to unlabeled examples. Compared to before, when we were using a single image as a query, now we can see the queries to be all the examples, all the labeled examples of a class. And we do this for all classes. At the end, the goal is to use these predictions as pseudo-labels and train a classifier. So at high level, we're trying to exploit the result of transductive learning to improve inductive learning. Now let's go back to our favorite toy example and see how this process works. Here we're dealing with 3 example classes and just a low number of labeled examples per class. We compute manifold similarity with respect to every class. This gives us a probability distribution for every unlabeled point. Simply by the argmax, we label all these points. And this is still at iteration 1. We iterate more and more until convergence. And these are the final pseudo-labels for all unlabeled points. So the method that we propose starts with initially training with all the labeled examples. This is not to provide an initial classifier, but actually to provide the representation model that is internal to this classifier. Therefore, we can map images to the representation space, use manifold similarity, perform label propagation, and with obtained pseudo-labels, we can retrain the classifier. And of course, this can be performed iteratively, because while retraining the classifier, we have an improved representation model. We go back to step 2 and improve the pseudo-labels and so on. One reasonable question is, whether we need this label propagation approach, and why not to just rely on pseudo-labels that are directly provided by the network classifier, which is actually a common approach in the literature. The intuition here is that the result of this label propagation is much more complementary. It's different than what the network can already recognize well. In terms of the impact on classification accuracy in a semi-supervised learning setup, we see that the benefit is larger in the low-shot regime, meaning where we have just a few examples per class that are labeled. Also, there are other methods in the literature that perform some kind of regularization during the training on unlabeled examples, and intuitively and also demonstrated in practice experimentally, we see that these methods are complementary to ours, and someone can easily combine both. Now, in the last part, I'm going to talk about a slightly different classification task. Again, we use the concept of ranking on manifolds to perform object discovery, so that we improve classification when we're dealing with few clean and many noisy training examples. And let me describe what that means. So for every class of interest, we are given a set of clean images. In the extreme case, just a single image per class. And we call them clean because we can rely. These have a reliable label. And using the class name, we assume access to web image collections. And with text crawling, we collect another set of noisy images. And these are images that are assigned to this class, but we cannot rely on their label necessarily. And we see all sorts of problems there with polysemy of the class name, with objects in different context, form, etc. And the goal here is to train a classifier while exploiting both clean and noisy examples, while benefiting despite the large amount of noise in the dataset. Again, the proxy task that we define is to try to identify how on which noisy examples we can rely on. And we formulate this as object discovery to estimate a relevance score for every noisy image with respect to the class. So first step, as before, we construct the k-nearest neighbor graph. Now we do this processing per class separately. We follow a slightly different way than before. Instead of just propagating similarities from the clean images to the rest, we want to take advantage of the fact that the noisy set typically includes a large amount of negative examples, and some of the negative objects tend to repeat. So instead, we train a graph-based classifier for a binary classification task. We have two classes, and we're treating all the clean images as positives, while all the noisy images as negatives. But there is a different balance, a balance factor that treats differently the two losses. And we cross-validate this in our experiments and get intuitive results. When the training is done, we make predictions on the exact same training set. So it's once more a transductive setup. Predictions only for this closed set of training examples. And we treat the scalar output of the classifier as a relevance score to the class. What we expect is that noisy examples that are strongly connected, that have a short path to clean images, will get also high relevance score. And then we simply use this score as a weight of a training example to train the classifier. And we use standard methods to perform this classifier training. Now just briefly looking at some results when we have only 1 or 5 clean images. Initially, we see the performance that is obtained just by training on the clean images. Then a reasonable baseline approach is to include all the noisy and treat them as clean as well, which indeed improves in the extreme case of having just 1 clean image, but not when we have more. Another reasonable baseline is as a relevance score and as a weight to use Euclidean similarity, which does not necessarily improve the case in all setups, which happens with the proposed approach when we use the output of the graph convolutional network as a relevance score for the noisy examples. So this brings me to the end of the talk. And just to summarize, I talked about how to use manifold similarity for the task of visual search. It is a more costly similarity to obtain, and speeding it up matters. Therefore, we propose some approaches for that, and also how to use a similar concept of manifold similarity to perform object discovery and facilitate different tasks that are dealing with low amount of labels or no labels at all. And so it turns out that such a manifold similarity was a useful tool in this process, and the applicability, the application domain is quite range. So we were dealing with representing images or image regions, but one can even represent pixels. Nodes are now pixels, connecting different pixels of an image or across images or different frames of videos and so on and so on. Thank you for your attention. I'm just switching to the last common slide with the brief characteristics.
Thank you very much for a nice, interesting lecture on visual search and object discovery. Now I open a public discussion to the topic of your lecture and asking audience for questions. Yes, Professor Kittler.
Thank you. Thank you very much for an interesting lecture. You mentioned very little about representation. Can you say a few words what you actually used and how the state of the art moved forward and whether it's still relevant or what the direction we see now?
Okay, thank you. Actually, designing representations and representation learning is also a large part of the thesis, but today I did not include our work on that. So in the work that I described today, we were often relying on a deep, in all cases, we're relying on a deep convolutional network to represent images. So, for instance, for the earlier work, because it was the times when we were often using deep networks to perform transfer learning. So we had networks that were trained on a very generic task. ImageNet was the breakthrough, and there were some models trained on ImageNet. So in the earlier work, we were just using these networks to represent images, so one can easily obtain internal activations of the networks and treat them as high-dimensional vectors in some representation spaces. So in this earlier work, we were using this kind of representation. Later on, it was also our own contribution of how to collect training examples for a task of representation learning, where especially when we're dealing with particular objects, by particular objects we mean that every distinct object of the real world is a different class. That's the case of searching for particular buildings or landmarks, as I described. So there we have seen that it's not necessarily useful to have training data with discrete class labels, meaning have labels that we normally use for classification. It was much more useful to have pairs of relevant and non-relevant images, which is much more costly to obtain with human-level supervision, to ask humans to annotate pairs of images. In this category, one of the contributions that I mentioned falls that we were trying to automatically do that. In another earlier work of ours, we were relying on other automated computer vision methods that perform 3D reconstruction. And with this rich information of the geometry of a 3D model, one could use to identify pairs of images that indeed depict the same object or not. So this was one of the contributions that allowed to create large training sets to create representation models for such a visual search task. The story can be long nowadays because of application domains that are very wide, many different domains and applications. Self-supervised learning seems to be very useful, how to train representation models without relying on labels provided by humans. And there is all sorts of work that try to do that, often achieving inferior performance than fully supervised, sometimes achieving even better performance than supervised models by human labels. And the message there is that often fitting to human labels is not a good way to generalize.
Well, thanks. Actually, a follow-up question. So what's the trade-off between representation and the need for measuring similarity on a manifold? Because if you had a very powerful representation method, you would map all the points from the manifold into a single point, and then you could use Euclidean metric or measure. Right,
that's true. It actually, even in our own work, where we're trying to imitate what manifold similarity indicates, and map images with high manifold similarity to nearby points, even then we observe that manifold similarity can still be useful. How do we observe that? By performing such a ranking and seeing that this improves retrieval performance, which indicates that still Euclidean distance is not necessarily a good measure. So it seems that maybe to some extent, because of all the different ways that objects can vary in the images, as I mentioned, different viewpoints, illumination changes, many parts can be occluded, we can see different parts. So it seems that, especially someone can imagine the extreme cases of very large objects, it's kind of very difficult and maybe not even desirable to map them to the same point in the representation space.
Okay, thank you.
I just want to go back to the previous questions, which I think you answered differently. Professor Kittler was asking what the representation is, and you answered how it was obtained by supervised. So I thought the answer would have been something like, we started with 500-dimensional vectors, now it's 1,000-dimensional vectors. So what is it, not how it was obtained? You know, you were explaining how it was obtained, supervised, semi-supervised learning, metric learning, but you didn't say anything about what the representation is, to give us some idea of the dimensionality, for instance.
Okay. I can add this up, but I thought that the question was also mentioning a part where, you know, how the field progressed and what is our contribution to obtaining this representation. That's why I took that path. But other than that, we're typically dealing with high-dimensional vector in the range of 500 up to 2,000 dimensions. So, but still, which is high-dimensional representation, it's still efficient to compute Euclidean distance for data sets up to a reasonable size. But nevertheless, it is still meaningful to try to compress that even more and allow visual search to scale up.
Thank you. Other questions? Professor Havran.
I would like to ask you, how does it work, for example, for similar species, that you have like plants that are kind of similar, but experts recognize that are different?
Okay, right. So that's a good question. Actually, it's not included in the talk, but we have also some experience. We have worked a bit on that problem. So it's a common problem in the literature. It's called fine grain recognition, right? Where we were dealing only with, let's say, images of birds. We know that it's a bird, but then we need to classify to the particular species. And indeed, it can be very distracting. I guess you refer to this problem because there are species that really look alike. So in practice, a common way to approach that is by focusing on details, on parts, and maybe on not dealing with global image descriptors, not representing a whole image by a single vector, but trying to represent parts and match the parts. So because details matter, and someone needs to identify the parts that make the difference. Other than that, it is always like a task of interest to deal with this in a more efficient way, to represent image with a single vector and have efficient ways to do search or to classify. And in this case, someone really tries to rely on human level labels to the for the starting point. You need experts to identify to provide the labels and the differences. Nevertheless, an interesting fact in practice is that such data sets, after created by some groups and used for a while, then people identify that, oh, they have a noticeable amount of mistakes in the labels. So, and especially in fine grain recognition, someone might be looking on these mistakes with the kinds of approaches that work on that. For instance, like you need hard negative pairs, you need something that in the current representation space, it seems to match with, let's say, the class of interest, but it comes from another class. and you really try to push this apart and disambiguate. But the problem is that it's not actually from another class, from the same class, but it was a mistake in the labels. So fully rely on labels can end up with some problems. And that's the reason why the method for discovering pairs that I described, we also evaluated on this task, and it seemed that it was even performing better than some fully supervised approaches because it was not really locking on these mistakes of the annotation.
So you have an experience with higher dimensional feature spaces. How we humans like to have a global look at the things and kind of grasp what is going on there. Did you gain some experience in looking at many these examples in higher dimensional space, how to get some insight? I mean, the typical thing would be lowering the dimension and looking at it in 3 dimensions. But when you start at dimension 100, it's too far. Did you get some good insight and experience how to do the things? Thank you.
Okay. It's definitely an interesting task to try to get inside. For sure, a challenging one. So there are also tools such as the well-known TSNE that help you to try to visualize high-dimensional space in lower-dimensional. Nevertheless, these are non-linear, so there is a non-linear transformation of the initial feature space, and you need to try to understand also like all the different parameterizations, so it's a very tricky process even to use these tools. Just to use, for instance, simple PCA that is linear, and maybe it will, it will distort less. These are things that we have been doing, and actually also try to spot this kind of non-linear manifolds to, indeed, to some extent, you can observe if you project down to 2 dimensions.
Thank you. So do we have any other questions from our guests? No? So in that case, I close the public discussion. Thank you very much to Dr. Tolias for his lecture and the audience for asking a question. Habilitation procedure will continue by its still public part at the meeting room number 80. So I kindly ask Dr. Tolias, members of the committee, reviewers to move to the, and of course members of the Scientific Council to move to the room, and we will continue in 5 minutes.